Alright, so in 10.1, the theme is right triangle applications. There are various different types of right triangle problems and scenarios that you need to be comfortable with in this section. A lot of it is review also, but we'll go through some scenarios and talk about some of the harder stuff as well. So one of the things that you need to be able to do in this section is solve a right triangle. So for instance, if I gave you a 30-degree angle, and I told you that this was 25, then you should be able to find missing angle and then the two missing sides. Okay, so basic theme is SOHCAHTOA, which we've talked about many times already this year, and you can use that here. So if you do sine 30 degrees, that would tell us the opposite over hypotenuse. And if I wanted to find the adjacent, I know the hypotenuse, I have adjacent, or I want to find the adjacent, so that's cosine. So cosine of 30 degrees equals x over 25. And lucky for us, these are unit circle values, so we know these. If it's an angle like 34 degrees or something like that, then we would use the calculators to get an approximation. Okay, but since we know what sine of 30 is, that's 1/2, which equals y over 25. Multiply by 25, so then y would be 25 over 2. If I take the cosine equation, we know that cosine of 30 is root 3 over 2. Multiply by 25, so we get 25 root 3 over 2 equals x. Now I suppose if you remembered your 30, 60, 90 shortcuts, by the way, the other angle is 60. I think we all can agree to that. If you remember your 30, 60, 90 shortcuts, then you could have found the short side is half of the hypotenuse. I mean, that's what we ended up getting. And then the long side, which is across the 60-degree angle, would just be the short side, which is 25 over 2 times root 3. Okay, so you can use those rules too if you would like, or just do SOHCAHTOA. In addition, you'll have word problems. Stuff that you did in geometry come back in this chapter, just as a review. So you know all those questions like, we have a ladder leaning against a building. Let's say the ladder is set up 10 feet away from the building. The angle of elevation is maybe 35 degrees. We want to find the height. Okay, so we won't talk about every single problem, but as long as you remember how to read the information and set up an equation, then you should be good. Okay, so if we're looking for height in relationship to the 35-degree angle, this is the opposite side. The 10 that we know is the adjacent. So if I'm thinking about SOHCAHTOA, that tells us to use tangent. So tangent of 35 degrees would be, let's call it h for height, over 10. You can multiply 10 with tangent of 35 degrees to get your height. And if you type that in the calculator, let's make sure you're in degree mode. 10 times tangent of 35 is approximately 7.00. So about 7 feet. Okay? There's a lot of other scenarios too. We should probably quickly talk about angle of elevation, which is really the same as angle of depression. And what you need to know is that these are always with respect to a horizontal axis or line. So for instance, in this triangle, we would say that this is a 35-degree angle of elevation, because here's my horizontal line and here's the angle. So this is an angle of elevation. There are some other problems where maybe, there's a plane flying around. That's not a very good plane, sorry. Maybe there's an angle of depression. So if I tell you angle of depression is, let's say, like 12 degrees, then what that means is that if you follow the line of sight to your target, or whatever it is that you're looking at, the angle of elevation, in this case the angle of depression, you need a horizontal line in the picture. So the angle of depression would be right here. Okay, a lot of times students will draw a triangle, like for example in this scenario. Sometimes they'll draw a triangle like this, depending on what the context of the problem is, and they'll put the angle of depression incorrectly right here. But this is not angle of depression, because this is with respect to the line of sight and a vertical line. Okay, so you always need to make sure you have a horizontal line in your picture for angle of elevation or angle of depression. Okay, so that's kind of your quick review of SOHCAHTOA problems that involves drawing pictures maybe and labeling some triangles and stuff like that. All right, now we're going to do some other applications. So one of them would be finding the area of non-right triangles. We already know that the area for a triangle, if we have the base and if we have the height, is 1/2 times base times height. Okay, so now the scenario is going to be, well, what if we don't have the height? What if all we have is this base and maybe this other side, and then we know the angle in between? Okay, so if we're given this setup where we have two adjacent sides, we know the angle in between, and we want to find the area, well, we need to find the height. Okay? We can find the height if we know A and we know B and we know theta. There's a right triangle right here, let me redraw it, that has A in it, and it's got height and theta. This part down here is part of the base. It's maybe half, it's maybe, we don't know. I mean, in my picture it looks like it could be half, but it's not necessarily true. Okay, but this for sure we know. We know this side A, and we want to find this height. So if we know theta, we have opposite, right? Hypotenuse. That tells us that sine theta would be the opposite, which is h over a. So the height can be written as a times sine theta, which allows me to now say that for this triangle, the area, which we know is 1/2 base times height, is going to be 1/2 times base, and since we know the height is going to be a sine theta, we can plug that in. And now this gives us an alternate area formula for non-right triangles, which is area equals, if I just kind of switch the order here, 1/2 AB sine theta, where A and B are sides that are connected or adjacent to each other, and theta is the angle between the two sides. Okay? Quick example. Let's say we have, this is 19 feet, this is 60 degrees, This is 10 feet, and I want to find the area. And I don't know the height, I don't know anything else. Since we have the two adjacent sides and the angle in between, I could go straight to the formula above, which is 1/2 AB sine theta. So 1/2, I'll say this is A, and I'll say that 19 is B. 60 degrees means I'd use sine of 60. So we have half of 10 times 19. So that's going to be 190 divided by 2, which is, what was that, 95 sine 60. And if we did not know sine 60, we would use our calculators, but that's unit circle stuff. Sine of 60 is root 3 over 2. So then we can just write this as 95 root 3 over 2. And since we are in feet, the units would be feet squared. Okay. All right, let's see. Just doing as many applications as I can. Oh, here's another one. Definition first. A segment. Not the traditional segment that you're used to. Okay? If I draw a circle, and we have a central angle theta. If I connect the chord from one part of the circle to the other, this little piece between the triangle and the circle itself, that's what we mean by segment. Okay? So it's the region bounded by an arc and its chord. Well, from what we've talked about so far, we can find areas of these things now. So here's an example. Let's say that, sorry, that's a bad central angle, but let's say that this is the center and that this is a 70-degree angle. And let's say the radius of the circle is 4 centimeters. And we want to find the area of the segment. So we're looking for this little piece here. Okay, well, this isn't too bad. Here's the basic premise. This whole wedge, this whole piece of the pie, so to speak, that's surrounded in orange, so the arc and the two radii, that was called a sector. Okay, so if we do the sector area, which we learned a few units ago, and then subtract the triangle that we have with the 70-degree angle and then the 4 for the radius, we also know that this is going to be 4. The difference in the large area, which is the sector area, minus the area of the triangle, that gives us the area of the little segment that's in the circle here. Okay? So, if you've forgotten, sector area is 1/2 r squared theta. And to find the area of this triangle, we either need to know the base and the height, which we don't, or two adjacent sides, which I do, 4 and 4, the angle in between. So now we can use the new formula that we learned, 1/2 AB sine theta. Okay? Now, if you've forgotten the rules with sector area, this 70-degree angle is bad, because whenever we use these formulas, this needs to be in radians. So let's convert it. To convert it to radians, we take 70 degrees, multiply it by pi over 180. So this is going to be 7 pi over 18. Okay, so we're going to do 1/2 r squared, which is 4. The angle, which is 70 degrees, we convert to radians. That makes it 7 pi over 18. Minus 1/2 A and B represent the two sides of the triangle next to each other, which is the radius, so 4 and 4. And then we do sine of the angle, and really it doesn't matter how we write it. Since we converted this to radians, let me just do it in radians, I guess. Okay. Now, since this is not a nice angle on the unit circle, we can just use our calculators to get an approximation. So if we type this in, we do 1/2 times 4 squared times 7 pi, over 18, minus 1/2 times 4, which is 16, times sine, and now let me check my mode. I remember earlier I changed it to degrees. I'm going to go back to radians since I wrote everything in radians here. This will be sine of 7 pi over 8. Oh, hold on a minute. This should be 18. Caught my mistake there. And if we type that in, we get that this is about 2.26 centimeters squared for the area. Okay, so that's one application of using the new area for a triangle formula. Okay, we got two more problems that we'll do real quick. Okay, so here's one more. Let's say we want to find the area of a regular pentagon inscribed in a circle. Okay, so first, let's draw a picture. So circle, inscribed means that the pentagon is inside. Regular means that every side length and angle is the same. So I'm just going to draw 5 points on the circle that are somewhat spread out evenly across, so that I can draw a nice pentagon. And if we're looking for, let's say, find the area of a regular pentagon inscribed in a circle of radius, I forgot to give that to you, radius 3. Okay? So for this problem, you can remember that we have 5 congruent triangles that create this pentagon. So if we know how to find the area of one of these triangles, we have the area of the whole pentagon. Because you could just do 5 times the area of one triangle. Now to find the area of one triangle, either I use 1/2 times base times height, which I don't have. However, I do know that the radius is 3. So each radius is 3, and I don't know these angles here, but since these are all congruent triangles, if I take 360, since there's 360 degrees in the whole circle, and divide it by 5, that tells me that each angle in here is 72 degrees. Okay? So, we can do 5 times the area of one triangle, which we're going to do 1/2 AB sine theta for that formula. So we have 5 times 1/2 times 3, and then sine of 72 degrees. And again, this is not an angle that we're going to use from the unit circle, so we'll just type it in the calculator. Make sure your mode is in degrees, since we're in degrees for this problem. So we have 5 times 1/2 times 3 times sine 72 gives us about 21.40 units squared for the area. Okay? All right, one last problem. This is kind of a harder geometry application problem, and it looks something like this. If it was a word problem, it could be something like, we have someone standing at this point looking up at something. They get an angle of elevation. Let's say it's alpha. They move back a certain amount, let's say 50 feet or 50 units. They calculate a new angle of elevation. Let's say that that's beta. And now what we want to do is find out what AB is in terms of alpha and beta. So now if we actually had a word problem, they would tell you, maybe this is 20 degrees and maybe this is 15 degrees. In which case, we'd actually have an answer. Since we don't have these angles given to us, our answer is going to have alphas and betas in it. And what we're looking for is the length from A to B. Okay, so at first glance, I see a right triangle here, and then a larger right triangle here. All right, let me call the big triangle ABC and the smaller one ABD. Now, what I can do is do a tangent equation. Say tangent alpha is going to be opposite over adjacent, so AB over BD. And for the larger triangle, from A, B to C, I could do the same thing and say tangent beta is going to be opposite, which is AB, over BC, which is going to be BD plus 50. So that now I have a system of equations. We have one equation, we have a second equation, and all we have is really two unknowns. We don't know AB and we don't know BD. Well, anytime you have a system of equations, the goal is to maybe substitute so that you can plug something into the other equation. Okay, and right now I'm seeing that maybe I could easily get AB alone. AB would be BD times tangent alpha if I multiply it over. So that now you could take BD times tangent alpha, plug it into this new equation for beta. So you have tangent beta equals BD plus tangent alpha over BD plus 50. So that now I just want to figure out BD. So before I had two equations and two sides I didn't know. I used the first equation, got something alone, plugged it into the second equation, so that now I have BD as the only thing I need to figure out. So I'll multiply the denominator over. So we have BD plus 50 times tangent beta equals BD plus tangent alpha. And if I want to solve for BD, I should probably go ahead and multiply this tangent beta through. So BD times tangent beta plus 50 tangent beta equals BD plus tangent alpha. And again, if I'm looking for BD, let's put the BD terms on the same side. So I'm going to write this as BD tangent beta, subtract BD to the left, and I'll get all the other stuff on the other side. So tangent alpha, and then I'll subtract 50 tangent beta. And now since the goal is to figure out BD, we can factor it out. So BD gets factored out, leaving us with tangent beta minus 1. And that's going to be tangent alpha minus 50 tangent beta. So then BD will be tangent alpha minus 50 tangent beta all over, if I divide now, by tangent beta minus 1. Okay, so that's BD. Remember, the goal was to find AB. So if I go back, right over here it tells me what AB is. Okay, so I could say that AB, which was BD times tangent alpha, I'll just take BD right here, tangent alpha minus 50 tangent beta over tangent beta minus 1. So that's BD, and then you multiply it by tangent alpha, and there is your formula for AB. All right, that is the end of the notes for 10.1. See you guys later.